Hello! Today, we're going to dive into the world of matrices and explore two very important concepts: inverses and determinants. By the end of this lesson, you will be able to first determine if a 2 by 2 matrix has an inverse, and if so, calculate it. Second, you will be able to apply the value of the determinant to understand a matrix's invertibility and the geometric relationship of vectors. These skills are fundamental in many areas of mathematics and science, so let's get started. First, let's understand what an identity matrix is. You can think of it as the number 1 in matrix form. For a 2 by 2 matrix, the identity matrix, denoted as I, is a square matrix with 1s along the main diagonal, from the top left to the bottom right, and 0s everywhere else. So, the identity matrix I is defined as this specific arrangement of 1s and 0s. Why is it like the number 1? Because just as multiplying any number a by 1 gives a, multiplying any square matrix A by the identity matrix I gives the original matrix A. This means that for any square matrix A, the product of A and the product of I and A both equal A. The identity matrix leaves the original matrix unchanged. This property is key to understanding the inverse of a matrix. The identity matrix plays a crucial role as the goal we reach when we multiply a matrix by its inverse. Now, let's talk about the inverse of a matrix. Just like we have a multiplicative inverse for numbers, like 2 times 1/2 equals 1, matrices can have an inverse. For a square matrix A, its inverse, denoted A inverse, is another matrix that satisfies a special relationship. That relationship is that the product of matrix A and its inverse, A inverse, is equal to the identity matrix I. The product of A inverse and A is also equal to I. So, multiplying a square matrix by its corresponding identity matrix results in the identity matrix of the same size. This is a fundamental definition. It's important to know that not all matrices have an inverse. An invertible matrix is also called a non-singular matrix. A matrix that does not have an inverse is called a singular matrix. Deciding if a matrix is invertible is our next objective. So, how do we know if a matrix is invertible? And how do we find the inverse? We use something called the determinant. The determinant of a matrix A is a single number, a scalar, that we can calculate from its entries. It provides crucial information about the matrix. For a 2 by 2 matrix, the calculation is straightforward. If our matrix A has entries A, B, C, and D, the determinant is calculated as A times D minus B times C. We multiply the diagonal entries and subtract the product of the off-diagonal entries. A common notation for the determinant uses vertical bars around the matrix. So you might see it written like this. Vertical bars around the matrix indicate its determinant. So, the determinant of A is equals AD minus BC. This number, AD minus BC, will tell us if an inverse exists. Take a moment to write this formula down. It's very important. Let's work through an example to calculate a determinant. Consider the matrix A with entries 4, 3, 2, and 1. Let's find its determinant. We use our formula, determinant of A equals AD minus BC. Here, I is 4, B is 3, C is 2, and D is 1. So we substitute these values into the formula. The determinant of A equals 4 times 1 minus 3 times 2. This gives us 4 minus 6, which equals negative 2. The determinant of this matrix is negative 2. The sign doesn't matter for invertibility, just whether it's 0 or not. Let's try another one. What is the determinant of the matrix B with entries negative 1, 5, 0, and 2? We apply the formula again. This is negative 1 times 2 minus 5 times 0. That's negative 2 minus 0, which gives us negative 2. So the determinant of B is also negative 2. Calculating the determinant is a crucial first step. It's the key to figuring out if an inverse exists. So, we've learned how to calculate the determinant. But what does that number actually mean for the matrix? Here's the most important connection. A square matrix A has an inverse if and only if its determinant is not equal to 0. This condition is a cornerstone of matrix algebra. If the determinant is any non-zero number, the matrix is invertible. If the determinant is exactly 0, the matrix is singular and has no inverse. Think about it like this. Division by 0 is undefined. In a similar way, if the determinant is 0, the matrix has no inverse. Let's check our examples. For matrix A, we found the determinant was -2. Since -2 is not 0, matrix A is invertible. We can find its inverse. For matrix B, the determinant was also -2. Again, not 0, so B is also invertible. But what about a case where the determinant is 0? Consider the matrix C with entries 2, 4, 3, and 6. Let's find its determinant. This is 2 times 6 minus 4 times 3, which equals 12 minus 12. That's 0. Since the determinant of C is 0, matrix C is a singular matrix and does not have an inverse. This is a very powerful diagnostic tool. Now that we know when an inverse exists, let's learn the formula to find it for a 2 by 2 matrix. The process is a combination of calculating the determinant and rearranging the original matrix. Here is the formula. It looks a bit complicated at first glance, but let's break it down. The inverse of A is equal to 1 divided by its determinant, all multiplied by a new matrix. Inside the new matrix, there are two key changes from our original matrix A. First, the entries on the main diagonal, A and D, have swapped positions. Second, the entries on the off diagonal, B and C, have changed their signs to -B and -C. So, to find the inverse, we follow these steps. First, calculate the determinant. If it's not 0, proceed. Second, swap the main diagonal elements and change the signs of the off diagonal elements. Third, multiply the new matrix by the reciprocal of the determinant. Let's apply the inverse formula to the matrix A from our previous example. Our matrix A is 4, 3, 2, 1, and we calculated its determinant to be -2. The first step, calculating the determinant, is already done. We know it's not 0, so an inverse exists. Step 2, create the new matrix by swapping A and D and changing the signs of B and C. We swap 4 and 1 to get 1 and 4 on the main diagonal. We change the signs of 3 and 2 to get -3 and -2. Step 3, multiply this new matrix by the reciprocal of the determinant. The reciprocal of -2 is -1/2, so the inverse of A is -1/2 times the matrix 1, -3, -2, 4. We distribute the -1/2 to every entry. This gives us our final answer. The inverse matrix, A inverse is -1/2, 3/2, 1, -2. We have found the inverse. A great way to check your work is to multiply A by A inverse and see if you get the identity matrix I. Give it a try on your own to confirm this. So far, we've treated the determinant as a number that tells us about invertibility, but it also has a powerful geometric interpretation for 2 by 2 matrices. A 2 by 2 matrix can be thought of as containing 2 column vectors or 2 row vectors. We can see the matrix A with entries A, B, C, D as having 2 column vectors, vector U with components A and C, and vector V with components B and D. These 2 vectors span a parallelogram. They are the adjacent sides starting from the origin. Imagine drawing these vectors on a coordinate plane. The parallelogram they form has its vertices at the origin, U, V, and U plus V. The non-zero absolute value of the determinant of A is precisely the area of this parallelogram. The determinant gives us a direct measure of the area enclosed by the vectors represented in the matrix's columns. This geometric interpretation gives us a new way to understand why a determinant of 0 means the matrix is not invertible. Remember the condition, determinant of A equals 0 if and only if A is not invertible. From a geometric perspective, this means the area of the parallelogram spanned by the matrix's column vectors is 0. For the area of a parallelogram to be 0, it must be flat. This happens when the 2 column vectors U and V lie on the same line. In other words, the vectors are parallel. If the vectors U and V are parallel, one is a scalar multiple of the other. The parallelogram collapses into a line and its area is 0. So, we can say that a matrix is not invertible if and only if its column vectors are parallel. This gives us a wonderful connection between algebra, geometry, and matrix properties. The determinant of 0 tells us 3 things. The matrix has no inverse, the parallelogram formed by its columns has no area, and its columns are parallel vectors. Let's revisit our singular matrix C from before. C has entries 2, 4, 3, 6, and its determinant is 0. The column vectors are vector 2, 3, and vector 4, 6. Notice that the second vector, v, is exactly 2 times the first vector, u. This means they are parallel. Their parallelogram has no area, and the matrix is singular. This powerful connection is a key takeaway from this lesson. Let's quickly recap what we've covered today. We started by defining the identity matrix, which acts like the number 1 for matrices. Then we defined the inverse of a matrix, A inverse, as the matrix that when multiplied by A yields the identity matrix. A times A inverse equals I. To determine if an inverse exists, we introduced the determinant. For a 2 by 2 matrix, the formula is AD minus BC. The crucial condition for invertibility is that the determinant must be non-zero. If it's 0, the matrix is singular and has no inverse. Finally, we found a geometric meaning for the determinant. Its absolute value is the area of the parallelogram formed by the matrix's column vectors. If the determinant is 0, the vectors are parallel and the area is 0. You are now equipped to tackle problems involving matrix inverses and determinants for 2 by 2 matrices. Keep practicing, and you'll master these concepts in no time. Thank you for watching.